So, using our log differentiation closed form expression along with our suitable high-order quadrature, we can now develop an expression for our stiffness integral. So, again, we have an expression that looks much similar to our module 2 low order. However, now we're replacing our basis functions in here from ramp functions to our Lagrange bases. And we can see that our associated weights on our Lagrange bases, as well as our velocity, is invariant of our integral. So we can pull that outside of our integral, such that we're only left with the inner product of a Lagrange basis with a derivative of a Lagrange basis. So unlike the mass matrix, even when we change our mapping from our physical domain to our computational domain, we don't end up having a Jacobian appearing. And this is because we actually do have a Jacobian here. However, because of the change of variables and the chain rule applied to the derivative of our weighting bases, we have 1 over the Jacobian appear out of that. So the 1 over the Jacobian times the Jacobian cancels out, such that no mapping is actually required inside of our stiffness matrix. We don't have any tricks that we can use with the Legendre points like we could with the mass matrix, so we're going to get a full matrix for our stiffness matrix. And this will be a square matrix equal to the number of points used in your interpolation and quadrature tall by wide. So we can imagine then to express this term here in a vector notation, we can get our stiffness matrix K here times a vector of our solution approximation coefficients times our constant linear velocity in our domain.